In this video, I'm going to explain some of the major scaling approaches being taken in crypto, including the approach Ethereum is taking with layer 2 and rollups, and how the modular vision for Ethereum and crypto more broadly fits in with this scaling approach. So as we know, every node in Ethereum processes every transaction itself. It doesn't trust some leader or authority to process transactions and then tell it the result. And of course, this is essential for the decentralization of the system. We also want there to be many thousands of these nodes all over the world in, varying network conditions and running on consumer grade hardware. So the question is, how do we scale this system? Because we can't just increase parameters. We can't just make the gas limit really high and the blocks really fast and kind of force the nodes to process more transactions. Because again, they're all over the world in the varying network conditions and they're on consumer hardware. So if you start requiring them to do 10x or 100x more transactions, the lower end machines in that bunch will fall behind. They won't be able to stay synced. And then the network will centralize again to a relatively small number of nodes. And if this is pushed far enough, if gas limit is raised high enough and blocks are made really, really fast, then eventually you get into a situation where the only nodes that can keep up with the network are running in data centers, because that's where the network conditions are best and where you want to have a really, really high-end machine running, because it has all the temperature control and all of that. The world's data centers are largely owned by like 3 companies, so you kind of defeat the whole purpose again. And this approach doesn't even get you that much scaling. You can maybe get 10x, maybe 100x doing this at great cost, right? A huge centralization of the network to the few nodes that can keep up with that. We really need like 1000x or more to reach Valhalla, right? And so there's simply no way to have thousands of machines all over the world running mid-range hardware and doing, thousands of transactions per second, especially when the state tree is really large. So this is one of the most basic approaches to scaling, and it has a lot of problems with it, but this is the approach that some chains are taking, right? So BNB, Binance Smart Chain, has done this. They forked Geth, they forked Ethereum, and made the blocks really fast and the gas limit really high. So they've achieved some scale by doing this, but centralized the network quite a bit. Polygon Proof of Stake is doing this to some degree as well. They have the same gas limit, I believe, as Ethereum, but they have quick block time, so 2 seconds instead of about 13 or so. And the fact that Polygon has a relatively small number of validators is probably at least partly due to this quicker block time. You do need a higher end machine to keep up. And it's a similar situation for Solana, of course. Relatively few validators with very high end requirements for the machines. 128 gigs of RAM, recommended 256, 16 core CPU, etc. So if the most scaling we can get out of a chain before it becomes centralized is like 10 to 100 TPS, then maybe we should have many chains and bridge them together. So what if we had, all these chains here, say they're all doing like 10 to 100 TPS, they're decentralized enough, we bridge them together, and then we have like hundreds of chains doing 10 to 100 TPS, and we have, thousands of TPS total. And this is kind of the approach that Cosmos is trying to take. They're trying to create this ecosystem, this constellation of chains. They call them zones. They're each independent systems, independent blockchains, but they bridge together really easily. So you can have, hundreds or thousands of zones, each of them doing like 10 TPS or 100 or whatever. And then they bridge together, and in aggregate, you get your thousands of TPS. The problem with this approach in general is that you're splitting the security of the systems, right? So if you have Ethereum and Solana, for example, and they're bridged together, that's great. But they're splitting the security because you have 2 different validator sets and 2 different chunks of staked assets on each chain validating those systems. And this is how Cosmos works too. Each zone in the constellation of zones is responsible for its own security. This is going to change in the future. They're going to have a shared security model, which will be optional for the zones. But for now, the security is broken up across all of these zones in the constellation. And another problem with this approach is that bridging is hard. And because bridging is hard, we have these hacks that happen, right? 625 million worth of ETH recently. There's been many others. There's 170,000 ETH, which is quite a bit. And this is kind of because these bridges as they are now they're honeypots, right? You have a huge pile of assets locked up in a smart contract that's serving as the bridge. You lock them up on one side and mint on the other. And it's a giant honeypot, which is part of the reason why these things have been hacked. An alternative to having multiple chains with the security split across them is to have multiple chains with the security shared, right? So this was the approach that Ethereum was originally taking with sharding. Each shard is essentially a copy or a clone of Ethereum in a sense. They run in parallel. So it's kind of like you have, in this case, 64 like independent little chains. And they're coordinated by the beacon chain, so they share validators across all of them. And the validators are shuffled in this way that allows for all of the shards to have, in a sense, the full security of the entire system, in theory. And this is essentially what Polkadot is doing, except instead of many shards, they call them parachains, and they're coordinated by a relay chain instead of a beacon chain. But it's the same idea. You have many of these chains, and they have a shared security model. Now, rollups are a sort of evolution of this multi-chain vision with the shared security of sharding, except instead of splitting up the validators and sharding the L1, you have the L1 verify or enforce the correctness of the execution of these other chains, which in this case are layer 2s, they're rollups. So at a high level, what we can have with rollups is hundreds or thousands of rollups all plugging into and interoperating through the L1. So the L1 becomes kind of like the beacon chain where the rollups are shards, or kind of like the relay chain where the rollups are like parachains in the Polkadot paradigm. And because the L1 is sort of verifying the execution on the L2s, or at least enforcing the correct execution, you can kind of think about it like the L2 activity is being compressed onto the L1, which is why I've drawn this diagram showing these layer 2s up here kind of being like compressed down onto the Ethereum L1. But unlike sharding, where every shard has to conform to the EVM, or it's created with certain constraints, whatever those might be, with layer 2, with rollups, each rollup can essentially take whatever trade-offs it wants. It can have any virtual machine it wants. It can use any smart contract language it wants. Like you can do layer 3, so you can have a layer 2 that has a rollup on top of it. So you can do layer 3, layer 4. Starkware people talk about this a little bit. And you can do, you can do like zero knowledge, full privacy, which is what Aztec is doing, I think. But there's this wide open design space where the rollups can take whatever trade-offs they want because they're decoupled from the L1. And we can then just see what works. We can allow the free market to decide, which rollups are making the right decisions, and we can let this natural evolution take place. And this, of course, is the scaling approach being taken by Ethereum. Sharding of the L1 probably won't happen now, or if it does, it's years away. Instead, Ethereum is all in on rollups. So layer 2 is the scaling path for Ethereum. And there's no major change to Ethereum that we need to wait for to unlock the scaling of rollups. Like the rollups are already here, they already work, the fees are pretty low. And as these rollups continue to optimize and expand and build out, we get more scaling. We don't actually need much to change on the Ethereum end. There are some changes coming later which will help make rollups a lot cheaper, like Danksharding, which is a replacement for data sharding, and then EIP-4844. These are just going to make rollups, cheaper, and a lot cheaper, but we don't need them really. Rollups can achieve huge scale right now with the current Ethereum. And, contrary to maybe popular belief, the merge proof of stake actually doesn't have much effect on scaling. Now, because rollups introduce this fundamentally new way of scaling, where we change the way we use the blockchain and achieve this kind of compression, because this is such a fundamental change, we have to rethink quite a bit about blockchains in general. And this brings us to the modular approach, the modular vision for Ethereum and for crypto more broadly. This modular chain vision is a relatively new concept, described best by Polinia on Twitter and Medium. I find the modular vision to be pretty compelling. This feels like a fundamental reimagining, restructuring of crypto. And I do think we have to go back and kind of, almost relearn the whole field, because this concept in rollups of verifying computational work without executing it is one of those fundamental changes or breakthroughs. So in this diagram, I'm attempting to illustrate how Ethereum can be thought of as having these modules and how you have a layer 2 kind of interacting with them. I'll explain this diagram in more detail in the rest of this video, but just a quick overview. So down here, I've got kind of the core Ethereum. This is the L1, so to speak. And above that, I have this layer 2, right? So I've got these 3 roll-ups up here. Each roll-up has a state and execution. This is the state, right? So it's got this grid of data. The state is all of the contracts, all of their data, all of the accounts and that data. Attached to this state is a virtual machine. The virtual machine is responsible for mutating the state, for processing transactions and computing how the state changes as a result of those transactions. And all of these systems do this. And in fact, as I've said before, this ability of these systems to have data, to keep track of some data, and change that data as a result of transactions according to some rules, which are defined in the contracts and the virtual machine itself. That is kind of the purpose, or it is the purpose of all of these systems at the end of the day. At the end of the day, what we want to do is to be able to have this world computer where you have data and it changes according to some rules. So each of these rollups has its own state and its own virtual machine. And you may notice that this virtual machine here on the left here is pretty much identical to this one down here. And this one down here is the EVM because this is the Ethereum layer. Now, I've just done that. I've made them almost the same because I'm just trying to show here that a rollup can have an EVM compatible virtual machine. It can have essentially an identical virtual machine. So maybe this rollup here is Arbitrum or Optimism. Other rollups, of course, can have a different virtual machine. They each have their own state, of course, but they can execute changes to the state using a different methodology, a different virtual machine, a different set of rules. And so I've drawn these two. You'll notice they're fairly different. They have this kind of like polynomial here, and they're slightly different structure, a bunch of constraints here. These I'm just trying to illustrate that they're different, and these ones are zero knowledge rollups. So, and I'll talk way more about that in future videos, but yeah, so you have these rollups and they're operating up here. Now they're kind of like attached, tethered. They're kind of like compressed onto the L1. What I'm trying to show there is just that each of these rollups has an associated contract or set of contracts on the L1 that is responsible for settlement, for settling the state of the rollup every 5 minutes or 5 hours or whatever it is. So these rollups are kind of attached to Ethereum here. So Ethereum, it has a couple different modules here. This is the state and execution of Ethereum. So of course it has the state, it has the virtual machine, I already talked about that. And so Ethereum is in a sense offering this as a service. This is the core service of Ethereum, is state and execution, right? That's the whole point again. But below that here, we have this giant cube, and this cube is meant to be the blockchain, just illustrated in cube form instead of a big chain because it's more compact. This blockchain, really, the blockchain is just there, as I've said, to kind of support the state and execution functioning of the system. But you can also use the blockchain as kind of like a storage medium, a storage device if you really want to. It's extremely expensive to do that, but you can do it, right? Because when you create a transaction to Ethereum, you have a bunch of data in that transaction, right? And generally, you only put data in there that you need in order to execute the transaction properly. If you're doing a Uniswap trade, all you care about is changing the state of Ethereum. You want to change the state specifically of your account to have more of one token and less of another token, right? And so you put data in that transaction, but only the data that's needed to execute that transaction. But there's nothing stopping you from putting some random data in a transaction and sending it to some function on some contract that maybe just does nothing. Ethereum does have this kind of side effect service that it offers where I can like just put some data in a transaction and have it mined, and then it's in the blockchain. And other people will easily be able to find that data, and I can't revert it and so on. You know, this is actually, you might wonder why you would want to do that, but this is actually a service that rollups use. Rollups have some data. They have some data that they produce regularly that needs to just be available to other people, and it doesn't actually have to be used in the execution of the settlement here, which I'll explain later. So what we get here is we have the state and execution module in Ethereum, and we have the data availability module. So kind of underpinning those two modules, we have the security and consensus of the system. And so I've drawn that here. You'll see these are meant to be Ethereum nodes. So there's like a grid of like 20, 30 Ethereum nodes, and each of them is like a complete copy of Ethereum, like the larger system. And some of these nodes are mining, right? So I've drawn little, like, these are meant to be little ASICs, and they're pulling power from the grid. These miners running these ASICs, they spend a bunch of electricity, a bunch of power on these blocks. They're like sealing these blocks. They're making them hard to revert, right? And then when the block is complete, when it's fully mined, goes into the blockchain, right? So we've got this conveyor belt kind of thing going on here with a bunch of these blocks. And finally, last piece of this is the roll-ups. We have this little like Christmas light thing going on here. These roll-ups are periodically settling, as I mentioned. So they're sending transactions, they're sending data to the Ethereum L1. They're, creating these transactions. They come down to the L1, they end up in blocks, they get mined, and then they're part of the data availability layer of Ethereum. And because some of the data in these transactions are in fact mutating the state, they're also using this state and execution layer for settlement. I'll go a bit more into rollups now, but first I just want to talk about this holographic computer concept because it's super cool. In the case of a system like Ethereum, we can think about it like it's one computer. It doesn't have a specific location. There's not actually one computer somewhere that represents the entire Ethereum system, so to speak. But, we treat it as a single logical computer. It has a certain state at any given time. It doesn't have 50 different states. It has a state. It has a certain history, and it has a certain set of contracts, which are, little code programs on this world computer. So at any given time, Ethereum is this like cohesive, coherent machine, this computer, this Turing complete system that really does function like a computer. We can send jobs, like we can send it code to execute on these certain programs. Again, like where does this world computer, like why do we call it a world computer? Where is it? Like we have to think about it in this different way as being this kind of world computer thing that's sort of like, it's like a computer in the sky or something, because it doesn't have a location. There's no single machine that's responsible for it. One way to, think about its structure is as being holographic. And one description of what makes a hologram that I've heard is it's where every piece of the whole is identical to the whole, right? So you have this machine where every subcomponent, every piece of the machine is actually just a complete copy of the larger machine. So it's this like fractal thing sort of where at the highest level it looks like whatever it looks like, and you zoom into the lowest level and it's like the same, it looks the same. And that is how Ethereum is architected in a sense, and all of these systems, right? You have this collection of maybe thousands of nodes, And each node is just a copy of the bigger thing. Each Ethereum node, that's why I've drawn it this way, each Ethereum node has the copy of the state. It has this execution and state layer here. So it has the state, it has the EVM, right? Each node runs the EVM, and it has all the blocks. Each node, in theory, has all the blocks, right? These machines all working together create this super holographic world computer sky machine. And the way this kind of happens, like if you just took one of these machines, in isolation, running the running Geth, you wouldn't really have anything that interesting. It wouldn't be crypto, it would be software. It would be some code running, and you would have like an EVM, and you would have blocks maybe. Like it might be an interesting computer science project, but in order to really bring it to life and create this like the great sky computer, you have to unify all of these nodes, right? That's where the consensus comes in, right? When you introduce, and that was the big breakthrough that Satoshi made way back in the day, is when you have when you have proof of work or proof of stake, you have some way for all of these individual machines to like cohere and then project into the sky, into the ether, this like world computer thing, right? And that's the magic. That's the big significant difference between these systems and regular pre-crypto computing, is you now have this kind of new dimension where these systems they're like these holographic projections into the sky that everyone can use and like have visibility into and coordinate around, right? So, okay, back to the modular vision. So I'll talk about the modules in this modular vision in a bit more detail now. So remember, we have state and execution, data availability, and consensus/security. So I'll start with state and execution. And actually, first thing to say is most people don't say state and execution, they just say execution. But I think state should be included with execution. Like you can't really have execution without the state. What would you be executing against, right? And I think the state is just as crucial as the execution. Like they're the essential things, as I mentioned earlier. The state and execution are the core central goal of all of these systems is to have your state and execute against it. In the case of rollups, rollups are often described in this modular context as doing their own state and execution. It's the one thing that these layer 2 systems, rollups, validiums, volitions, which I'll mention later, the one thing they all do is they do their own state and execution. And what that means is that each of these systems, they maintain their own state tree. They have their own accounts and balances and all that stuff. They have this huge collection of data that represents the state of the system, and they maintain that themselves. In the case of Ethereum, the Ethereum state right now might be, let's say, 250 gigs. These rollups, right now they're probably pretty small, but in the future, these could each be like 500 gigs worth of state. And you could have, right now there's 3 of them, that'd be 1.5 terabytes of state. You could have, 100 terabytes worth of state. All the while, the Ethereum state could be, 300 gigs or 500 gigs or whatever. My point there is just that each of these systems, they're maintaining and keeping track of their own little universe, right? They have their own little world, they're like their own little island, just like the different chains in the multi-chain vision. These rollups, they keep track of their own state, and they execute against their own state. They have their own virtual machine, and the virtual machine receives transactions and mutates, updates the world state as a result of those transactions, and that's how the system functions. So clearly these rollups are handling their own state and execution, as I've said many times, but I've also drawn them here as connecting to the Ethereum L1 state and execution. So are they like kind of using both? In order to clear that up, Some people refer to a fourth module in the Modular Vision, which is settlement. These rollups are, in fact, totally maintaining their own state and execution. So users, the kind of interface that the users are interacting with is handled by the rollups. That's their accounts and the contracts and all of that, right? Ethereum is not doing that. But these rollups are using Ethereum's state and execution layer in order to settle. Rollups periodically will settle on the L1. What they're doing is, in the case of a ZK rollup, they're sending the validity proof to the L1. The L1 checks it, and the state is updated. And then the world can look to the Ethereum L1 and know that the history of that rollup has been verified by the zero knowledge proofs all the way up to like an hour ago. It's the same situation in optimistic rollups. They periodically, often pretty frequently, every few minutes, will settle on the L1. So they'll post their new state root, essentially the fingerprint of the new state. It's like, there's been 3 minutes since the last update. We've processed maybe like 5,000 transactions or whatever. And here's just a snapshot. Here's like just the state root. That's the result of those changes, the result of those transactions. And then in the case of optimistic rollups, people can challenge that claim by posting a fraud or fault proof. Or if that doesn't happen, then the state transition is accepted. Now, both validity proofs in the case of ZK rollups and fraud or fault proofs in the case of optimistic rollups are accomplishing the same thing. You're verifying or having some strong assurance that the transactions that are happening on this other system, that you're not really verifying yourself. You have some assurance that those transactions are being processed properly without executing them yourself, right? Which is the great scaling advantage of rollups. In all the other systems that I talked about, whether it's multi-chain or a sharded system or just a single chain where you crank up the variables, every node in those networks, they're processing every transaction, right? If they're not using rollups in some way. So there's fundamental limitations to the scaling you can get that way, obviously. And when you have this technology, this way of this asymmetry where you can verify the execution of like 1 million transactions in, a tiny fraction of the time it would take you to actually execute those yourself, you get some scaling advantage. These rollups, as they're sending these proofs or they're settling on the L1, they do that by sending transactions to the L1. And those transactions will consist of two kinds of data in a sense. So part of what they're doing is actually executing changes on the L1 state. In a kind of simplified case, an optimistic rollup, for example, might simply post a state root update. So every 5 minutes when they settle, they do want to change the Ethereum L1 state, but all they want to do is like change the state root in their contract, right? So here's the new state root as a result of the past 3 minutes of transactions. But they do need to include some other data because of the way optimistic rollups work, where you optimistically assume that state root that you've been given as the L1, you assume that state root is valid, but you allow for this challenge to happen where if some observer sees that transition actually wasn't valid, then they have the opportunity to challenge it, right? So in order for that challenge protocol, that challenge mechanism to work, there needs to be a record of the transactions. Because if there's a record of the transactions, we can prove that no, when you applied this certain transaction to the state, the resultant state root, the resultant, balance in this account or whatever, which trickles up to the state root, should be different. in order to resolve that dispute, we need all of the transactions to be available. So this is where the data availability, of course, comes in. A portion, and actually a pretty large portion of the data that's being sent to the L1 in the form of transactions from the rollups is just this data that needs to be just available. It needs to just be there. When this optimistic rollup sends its settlement transaction to the L1, by default, if there's no fraud resolution that needs to happen, the L1 will simply do a very little amount of work. It will maybe just update that state root. And in practice, it does a little bit more, but it'll do something very simple. All of those transactions, they need to be accessible in case there is some dispute to resolve. And they are compressed quite a bit, right? This is from one of Vitalik's posts where he's showing here that you can take a transaction which on Ethereum, regular Ethereum would take up a certain amount of data, like 112 bytes. On a rollup, when the transaction's actually happening on the rollup network itself, it may take a similar amount of data. But when you do your settlement onto the L1, right? You do your proof, you send the data, you send some transaction data because you need to have that record of all the transactions in order to resolve disputes. When you do that, you can compress it a lot, right? So this is part of the way optimistic rollups scale is you can compress these transactions to be pretty small, and you just put them into the data availability layer of this system, the L1. The L1 doesn't actually have to process those transactions. Those transactions don't actually act against the state. The EVM can essentially ignore them. Now in the future, when Ethereum has some of its coming upgrades like Danksharding and this EIP-4844, where we have a new transaction type which just straight up accepts data, right? You just put data in a transaction and you just send it to Ethereum. That data is never used to execute against the state. That is when rollups get a lot cheaper, because currently when we send this data to Ethereum that we just want it to be available, we just kind of want it to be stored. It's not actually being used to change the state of the state. That is a bit more expensive because we're using the Ethereum call data, and all the call data is when you do a transaction, you include a bunch of data, right? In your transaction, you specify obviously which contract you're calling, and that's just who you're sending it to. And then in your data payload, you'll specify which function you're calling, which takes like a few bytes, 4 bytes, I think. And then the rest of that data is the call data. And that is all of the info, all the data that you're giving to this function to execute whatever it's going to execute. And as I said earlier, usually we're including data in our transaction because we want that data to be used to execute, to change the state of Ethereum, because that's generally what we're trying to do. But in the case of rollups, as I've said, we have some data that isn't actually going to be used by the EVM to change anything in the state. It just needs to be available, right? Hence data availability. So again, in the case of optimistic rollups, this data that we're sending to this data availability service, which may be Ethereum, the Ethereum blockchain, this data is the compressed transactions. So every transaction that happens on the optimistic rollup has to be put into this data availability service, because again, to arbitrate a fraud proof, a fraud challenge, you need to be able to get that transaction data. But in the optimistic case, when there's no disputes, we don't actually need to look at that data. But the transaction data has to go onto the L1 in compressed form, which is what Optimism and Arbitrum do, of course. So we can see that this is the Optimism Block Explorer, and we can see the latest L1 batches. So these are batches to the L1, which is Ethereum, and you can see the L1 transaction is here. This takes us to Etherscan, of course, because it's a transaction on Ethereum. And if you look at the input data, this is the call data, the input data that the transaction has, and it includes a whole bunch of data. This data is transaction data, right? This is compressed transaction data. This is what Vitalik's referring to here, is this transaction data is taking up it's using only 12 bytes, maybe it's better now, I don't know, but it's using a lot less data than it would if it was a full transaction on Ethereum or even on the L2 itself in uncompressed form. But when the settlement happens, you compress it down, you ship this batch to the L1, and again, most of this data is we simply need it to be available. So it just goes into the chain and the EVM probably doesn't touch it. And the situation is similar with ZK rollups, right? ZK rollups post validity proofs to the L1. So there we have a different system. We prove that the execution has happened properly. So we have the old state root, right? The state was whatever it was. And now there's been like 100,000 transactions, let's say, and we have a new state. We have a new state root. And we prove that execution was done properly, right? That we didn't, make our balance higher without having a valid transaction doing that, right? We prove the correctness of that with a zero knowledge proof. And the associated contract on the L1 is the thing that executes and verifies that proof, but we still need to store some data. So in the case of ZK rollups, you actually don't need to store every single transaction because we don't have this kind of like dispute resolution thing where we have to drill down to like a single transaction to verify its correctness or anything like that. Instead, it proves the correctness of the new state. So you can actually just provide a state diff. All you need is, as a user, as like an independent verifier of the system, I simply need to be able to build up a picture of the state. I need to be able to follow along and have, up-to-date state, because I need to know what my transaction is. I need to know like what is the state of this random contract, because maybe there's like an Oracle price in there or something, right? All you need on a ZK rollup is you just need to be able to get the up-to-date state. And the easiest way to do that is actually just to take and say, here's the difference. So state A had, it's like 500 gigs. State B, there's been like 10,000 transactions, but maybe some of those transactions were back and forth between like just two accounts. In the kind of extreme case, you could have 100,000 transactions, but literally it was just two accounts sending like one ETH back and forth, or one whatever token, right? And if you wanted to put all that transaction data on chain in like an optimistic rollup, you have to include all of those transactions. So the 100,000 of them, right? In the case of a ZK rollup, all you need is, you just need to know what the new state is because it's already been proven correct. So you can have your diff in that case would be simply, there's just two accounts, they swapped balance back and forth, they swapped one token. And at the end of all that, maybe the account B has like the one token, or maybe account A has the token and it's back to normal, or it's back to the way it was before. So ZK rollups, they can potentially achieve a lot more scale, especially as the transaction throughput gets really high, because you only have to provide the diff, right? And the diff can be a lot smaller than all of the individual transactions. But either way, the ZK rollup still has to post that diff data to the data availability service. In the case of Ethereum, it's the same idea. As it stands now, that diff data for a ZK rollup is being sent in as call data. And in the future, it will be sent in as a data blob. Now, speaking of future upgrades, the current Ethereum system as it is now, it isn't really designed for data availability per se, because, for example, Ethereum nodes are not incentivized directly to store data for any real duration of time. As an Ethereum miner, you only really need the data of like the last maybe 100 blocks, just in case there's a reorg. So you don't want to have to like re-download stuff to start mining again. You don't really care about data that's like 2 weeks old. And in the case of, or for rollups, we need that data availability to, be there for some duration of time. Maybe it's like 30 days or whatever it is. But in future upgrades, this will be resolved where you have data availability sampling and direct incentivization to store data. But either way, the way to think about this data availability service or module is as this global bulletin board thing where we simply post data that needs to be available. You need to be able to get it. And we don't need the EVM, we don't need the virtual machine to process it or like check validity or anything. We just need somewhere to store data. So we can obviously do that, or it's a different set of trade-offs. We can do that much cheaper. Like we can store data and make it available much cheaper than we can take data and execute it against this huge state. That's where we can further scale rollups, because most of their cost today is actually just this data availability thing. Like they're posting quite a bit of data to Ethereum via this call data thing, right? And Ethereum doesn't really have a way to distinguish real call data that's going to be used to execute against the state versus call data that's just straight up just needs to be stored somewhere, right? So we can't reduce the gas price too much on the call data because, in the worst case, that it is actually expensive to have the EVM, process a bunch of data. And until we have this way to distinguish, until we have the data blobs, the blob transaction type in EIP-4844, when we have that, we can make those really cheap. It's just way easier. It's really easy for all these nodes in the Ethereum network, the L1 nodes, to just store data. Don't even really read it, just store it. In the future, this will be a lot cheaper and the rollups will scale a lot further. And speaking of cost, rollups actually have an interesting cost sort of model. So there's three main cost components for a rollup. There's the actual costs of running the rollup itself. So this is like the cost of running the sequencers, the operators. These are the ones who are processing the transactions. These are the ones who have that whole 500 gigabytes of state or whatever. They have all that. They're keeping track of it. And they're doing, 5,000 transactions per second or whatever. So this is some super powerful machine that's doing a lot of computational work that it's very hard for, a random consumer grade computer to keep up with. But they're doing a huge amount of work. And because of rollups, of course, we can verify that work is done correctly. So it's all good. There's no worry there that they're going to do something incorrectly. In the case of optimistic rollups, this is a little bit untrue because you do need to be able to have independent verifiers or independent nodes kind of watching, because then they need to be able to see if something was done wrong so they can start the fraud proof process. But in ZK, you can have this super powerful machine just blasting through transactions, and as long as those proofs check out, we're good. So there's multiple costs there, right? There's in all cases you have some sequencers, some valid or some operators that are doing the processing of the transactions. In the case of ZK rollups, you have to also generate the proof, and proof generation is pretty expensive. It takes quite a bit of computational power, but those costs are not too high in the big scheme of things. If you're doing thousands of transactions per second, running some super high-end AWS machines is probably not a huge deal. You do have to also pay for settlement you have these contracts on the L1, you're sending the transactions to them, and you are making state changes on that L1. At the very least, you're updating the state root. In the case of ZK rollups, they're verifying that proof. So that has a cost, of course. You're paying gas, right? You're paying for the use of that L1. But the biggest cost in rollups is actually the data availability. The transaction volume, in the case of optimistic rollups especially, every transaction you do is resulting in some data being sent to the data availability layer. You end up having to send a lot of data to that data availability. In the case of this optimism settlement transaction, there's like quite a bit of data there. And most of this data, again, is not being used by the EVM necessarily. It's really just being stored, like data availability kind of sense. And finally, back to security and consensus. So the security and consensus layer or module isn't really a discrete service as far as I can tell. Like, I don't know how a rollup could use the security and consensus portion of Ethereum without using the data availability or the execution layer, because, all the security and consensus layer does is ensure the correct functioning of the two layers above it. And more accurately, it's not really so much about the correct functioning. Proof of work, proof of stake, it does not process transactions. Like, that's not the main thing being done. So it's not really about verifying that, a transaction was processed properly or that a smart contract call was executed properly. That's kind of baked into the protocol itself. What the proof of work, proof of stake, security consensus is doing is more about ensuring blocks, transactions that the network can come to consensus on what the ordering of those are. And it's about deciding the order and about making it hard to change that, right? It makes it really hard to revert or to change history, to fork the chain successfully. This layer of security and consensus, it kind of underpins, it's like the pillar holding up the other two layers, but only in the sense of like their history and ensuring that we can all agree on the history. And that's really important for the layer one to function, especially when it's functioning as a settlement layer or as a money system, DeFi system. But when you start thinking about rollups, some of that stuff actually gets kind of fuzzy, which is why, to me, it feels like this modular vision that's been kind of unleashed by this rollup technology, this kind of changes everything potentially about crypto. Like, I feel like I have to go back and really re-examine everything. Like, all of the security assumptions and the way we think about, a 51% attack and so on. A lot of this stuff is very different when you think about rollups. For example, in terms of data availability, we don't actually need consensus so much on the data. Like, as long as the data is available, the layer 2 should be able to verify which data is proper, because we have proofs of these state changes, and it should be easy to tell which, if we have like a whole collection of these batches, which are posted to the data availability, you could throw in a few like invalid batches in there, and it should be really easy for the layer 2 nodes to detect that, because things won't hash out properly. So the consensus at the data availability layer is far looser. Like, we don't need the strict consensus that we need in a regular layer 1 blockchain, where like you can't have conflicting history. Things will just break, right? But in a data availability sense, with a layer 2, you can have a few extra batches thrown in there that are invalid, and it's probably fine. Which is why it's called data availability and not data like consensus or data security or something. Okay, so the last thing I'll talk about is this kind of growing ecosystem, this beginning of like a Cambrian explosion of these different flavors of rollups and rollup-like systems. So because we've split systems like Ethereum into these multiple modules, now these layer 2s can like mix and match different modules from Ethereum, from other systems which are dedicated modular systems. So for example, rollups are kind of the standard way to do this, where you, like I've described, you settle on Ethereum or on your parent chain. You use the data availability service of that parent chain as well. You kind of do everything on the parent chain. The rollup does its execution, of course, itself, but it uses the parent chain for everything else. And this is the most secure, arguably. In the case of Validiums, so this is a alternate way to do this. You have that kind of system similar to rollups, except for data availability, you use some external system. So now you're doing your settlement on the layer 1, the parent chain. And so the proof verification perhaps is happening there. So you can have high assurance that the transaction activity was processed correctly. But then the actual batch data, all those transactions, that data is being stored somewhere else. So you could store it on Celestia or ZK Porter, or there's a whole bunch of these that are developing now that are just specializing in data availability, right? Just try to offer the best possible data availability service that you can. So Validiums will often be cheaper because they're using some system that's cheaper for storing data. You then have, side chains and alt-L1s. Those are completely different. That's just a separate blockchain, and you have a bridge. It doesn't have any of the security. It's not a rollup. It's not a layer 2. Then you have volitions. They're like a mix between Validiums and rollups, where you use the execution, the settlement of the L1. So you're verifying your ZK proof there, or whatever it is. And the users can choose whether to store their data on the data availability of the parent L1 or somewhere cheaper. So now they can have the best of both worlds. You can, if you're doing some like activity that's not that important, you can use the cheapest available data availability. And if you're doing something like DeFi or some high value transaction within DeFi, then maybe you use the native data shards on the parent L1. Okay, I hope that makes some sense. As I said, this modular vision is complicated. There's a lot of nuance, and so I can't cover everything in one video. Maybe I'll do another one in the future. But next video will be more on rollups, specifically ZK rollups. So I'm going to go deep on that. So watch out for that. Subscribe. Thanks.